Hello and welcome to Imagine, a unique imaging-omic platform that allows you to correlate your imaging and omic features and build sophisticated ML/AI models off of it. You can create an account using Create Account button. This is a freely usable software hosted on the cloud of Queensland University of Technology. I'll start off by logging in into our lab's common Gmail account. Further, you can start the experiment by clicking on the upload file. Here, you can select from multiple model types, starting with linear regression, linear models, multitask lasso, decision trees, and more coming further in newer versions of Imagine. So let's start with the linear regression. Any details regarding the linear regression model and the parameters used therein could be found here. This is a section where you enter model parameters. For example, any parameters that you could think in case of, let's select a linear model here. So we can use alpha, for example, 0.8, CV equal to 2. Or you can keep it empty such that it uses the default parameters as the scikit-learn library uses in the link herein. You can select whether to do a grid search through hyperparameters, and the hyperparameters could be mentioned here in the form of going from certain values to the other, such that you could select a list of values for plethora of parameters that you wish to run your grid search through. For the sake of this tutorial, we'll just do with grid search false. And here in the mode, you can select between different modes: train, predict, validate. We'll go with the training. Here you can select your test size. So 0.2 indicates out of the total data set, 20% of the data would be used for test and the remaining would be used for training. This is a k-fold cross-validation splitter parameter that you could indicate to cross-validate the trained data set within itself. Setting it to 2, we move further. For the data type and label type, you can select whether going from imaging to gene or gene to imaging. Normalize method could be selected either same or different for data and labels. We'll start with stand scalar. Correlation method could be selected either of Spearman or Pearson, and the correlation threshold could range between -1.0 to 1.0. Setting -1.0 allows you to completely silent the correlation module here, such that you take all the features into the AI module. We'll start with the setting the correlation filter threshold filter as 0.7. Essentially, this is a correlation coefficient threshold filter that allows you to filter through high correlations and take only those features through the machine learning module. Further, you can select whether to correct the p-value for your correlations. So I'll go with the famous Benjamin Hodgbuck. Next, we input data and label features here. So one thing to keep in mind is that your input file name should have underscores or hyphens, preferably underscores, and should not contain any spaces in them, such that the software could intake them appropriately and operate through to get you definitive results. So here we would select, since we indicated data type as imaging, we would select radiomic.csv as data, and genefpkm.csv as our genomic feature file. And just to allude more how these files look like, these are essentially the comma separated values that could be opened up in Excel or could be prepped in Excel and stored as .csv, where they have a common ID column between both radiomic and the genomic or any other omic data file that you want to use. The features could be, the features could be genes or even patient outcomes that you want to train against. So one thing to make sure beforehand is the ID column is sorted in the correct order between the two files and should match exactly between the two files. This is the first test that the Imagine performs. If that doesn't meet the criteria, then Imagine will basically error out saying that IDs are not matching. So you would have to run them again. Taking it further from there, so once we have loaded the files, you have an option to choose whether you want to store the data for Imagine, which is highly recommended, as this tool is meant to democratize radio-omic or imaging-omic correlations and machine learning model across the globe, such that a consensus could be arrived at these models and radiogenomic reports thereof to be shared across multiple labs worldwide. So I would highly request you to select yes. If you still think you don't want to share the data, you feel free to do no. Model file could be left empty because this is a training mode where it would generate a model file for you. This option is to be used only when performing validation or prediction on the already cooked model. So here you could basically upload a pickle file, model.pkl, that you already generated through training of the model early. But for this tutorial, since we are going through the training mode, we will keep this empty. So once you submit and once everything gets accepted fine, it will give you an upload confirmation giving you the job ID, which could be tracked here as created, updated, and whether the task status is created and whether it's running or completed. As you could see that you could run multiple parallel experiments at the same time through Imagine using the cloud power, such that you get results around the same time and you could compare through different models or perhaps different experiments between different features that you wish to. So for the sake of timeline here, I've already downloaded a report which was pre-cooked using the same approach. And so here basically you would see two reports coming out of Imagine. One is with the correlation and the ML module. Another one is without the correlation module and the feature selection mode, which automatically runs through Imagine. So you don't have to worry about setting the feature selection mode here. Ideally, the report looks like this, where it gives you when the models were run, model inputs, multivariate correlations, the features selected post-correlation, imaging and gene features, what were the parameters that got finally used for model training, either with or without grid search, model evaluation for the trained data, just to peek into how the trained data look like, model evaluation for test data, where you have the scatter plots of actual versus predicted values for different omic labels that got predicted, the RMSE to standard deviation ratio indicating how well the model performed, some more matrices here giving you the observed mean and the ratio of RMSE to standard deviation, and finally the AUC values at different decision thresholds, aka the FPKM thresholds that were set here to predict the gene expressions at certain thresholds. So what happened was at each threshold, the data got binarized, the test variable got binarized, and it was evaluated whether how well it predicts the continuous gene expressions at each threshold using the imaging features, such that you could be confident that, for example, here at 0.5, the gene label ACTG2 gets predicted at a very high AUC value as opposed to 0.2, indicating that high expressions matter for this gene, versus some do go beyond 0.8 AUC for lower expressions. So this way you could connect the genes within the pathways post Imagine runs, and basically find the biological significance through looking through publications, whether other studies have reported the same, which we did, which is exactly the thing that we did in our manuscript. So please refer to that. Further, you have more validation data running permutations through each of these labels, only through the labels that have higher AUC, that is greater than 0.9, and R square greater than 0.25, such that you know whether this data is either randomly performing to be very accurate, or it's actually confident with the p-values, with the strong p-values that we achieved, which were even like less than 0.002, such that it gives you confidence in the label predictions using the imaging features. Further, there are text files available in the output folder that gets downloaded from the Imaging platform, where you could tally all the AUC results in the tabular format and work out your own plots if required. A nice wiki exists on our ImaGene's GitHub page, referenced on our manuscript. So it includes the entire flowchart of the Imagine workflow that gets performed in the backend, and description of each of the functions used in the Imagine scripts, starting with the Python main, to the processing, to the normalization, building model, and evaluating it. Further, if you want to run Imagine on a command line interface, you can download the Imagine's Docker container from here and follow the instructions exactly to run to load the Docker container onto your Linux or Mac platform, and run it as a command line interface exactly as shown here, using the test data sets that we had attached here for radiomic, FPKM, CSV files, as well as some supplementary material for you to look at to check on the results. Thank you, and I hope you have a good time running Imagine. If there are any questions, please forward it to me using my email ID on the authors list on the manuscript. Thank you.